So guys, are we live? Let me know in the chats if I'm audible to you. Let me know in the chats if I'm perfectly audible to you. Quickly, my dear people, quickly. Let me know in the chats if I'm audible to you. Yes? Just give me a second, I'll fix certain things and we shall be starting, yeah? Just give me a second, guys. Just give me a second, we shall be starting. Perfect. So, welcome back, all my lovely elites. Welcome back. I hope all of you are doing great, having a good time. So, quickly, just let me know in the chats. Quickly, just let me know in the chats if I'm perfectly audible and visible to every one of you. Quickly, let me know in the chats, my dear people. Yes? I'm doing great, thank you, thank you. Just let me know quickly, my dear people, if I'm perfectly audible and visible to you. Hello, Sahita. Hello, Deepu. Hello, Pranjal. Hello, Jan. Hello, Jumi. Hello, Dr. Manisha. Hello, Vishwa. Welcome back, everyone. Welcome back. Welcome back. Welcome back. Hello, Nikhilesh. Hi, Yuvashri. Hello, Pooja. All right, people. So, as you all must be knowing, tonight it's going to be our one more session for the IDOC series. Till now, we are done with the 2 blocks. In the last block, we were left with 2 chapters, and I've added those chapters in the today's block, right? Well, electrochemistry and chemical kinetics, we were not able to finish in the last session, right? So, in this particular block, we shall be doing 3 chapters. One is going to be a general organic chemistry. Then we shall be doing electrochemistry, and at the end we shall be doing the chemical kinetics, right? And I'm sure you guys know about how do we approach to this series, what all things we do in this particular series. Well, it is the very effective series to cover everything in lesser time, right? To revise everything in lesser time in the form of questions. Perfect. So, my dear people, before starting this particular session, the ones who have just joined in, the ones who are new to the channel, I'll just quickly introduce myself. So, my name is Wasim Bhatt and I'm your chemistry master teacher writer on this Vedantu and NEET channel, right? Well, the ones who have not liked the video yet, please do like the video, share the video with all of your friends, let every friend of yours, whosoever is preparing for the NEET 2022 examination, get benefited out of these sessions, right? So, do first of all like the video, and do share the video with all of your friends, and at the same time do subscribe to the channel as well. Okay, perfect. So, my dear people, let me quickly know in the chats if all of you are super duper excited about this particular session as well. Let me quickly know in the chats if all of you are super duper excited about this particular session as well, right? Let me know in the chats. Let me see the Josh of the session first, then only we shall be starting, right? Let me quickly know in the chats if all of you are super duper excited about this session. Yeah? Hello, Jan. Welcome to the session. Perfect, guys. Perfect. So, glad to know that, Vishwa. Glad to know that. That's great, Darshini. Congratulations. You got 97.18 percentile in JEE. 99.2 in chemistry. Wonderful. Good job done. Congratulations. Congratulations. Perfect. Well, I expected this from you. Absolutely. All right, people. So let's get going and let's get started with the general organic chemistry with the first question, which is going to be on your screen in 3, 2, 1, and now. This is the first set of questions, my dear people, which we are going to solve in the tonight's session. The question says, arrange the following in the stability order, right? arrange the following in the stability order. This is the first set of questions which you can get in your examination. And let me show you exactly how to deal with these sort of questions, right? First of all, what you need to remember is, whenever you need to compare the stability of the charges on different elements which belong to the same period. Whenever you need to compare the stability of the charges present on the elements, and those elements are, for example, belonging to the same period. At that point of time, we decide the stability of the charge on the basis of electronegativity. Do remember this is the first important point. Whenever you need to compare the stability of the charges on the elements which belong to the same period, we do that on the basis of electronegativity. 2 points which you need to remember right here. And what are those 2 points? Number 1, negative charge is more stable on more electronegative element. Negative charge is more stable on more electronegative element, and positive charge is more stable on less electronegative element. Positive charge is more stable on less electronegative element, right? The first point which you guys are going to remember from now onwards. In the similar way, my dear people, whenever you need to compare the stability of the charges on the elements which belong to the same group, you do not decide it on the basis of electronegativity. You decide it on the basis of volume charge density, right? This concept is for the elements which belong to the same period, and the concept which I'm going to tell you now, that is for the elements which belong to the same group, right? What is this volume charge density? It is basically the ratio of charge present on the species divided by size of the species. Perfect. Do remember one important thing. More the volume charge density, less is going to be the stability. In the similar way, lesser the volume charge density, more is going to be the stability. Now let's try to solve the questions, right, which are given to us. Have a look. Arrange the following in the basis on the base of the stability order. Have a look. Nitrogen carrying the negative charge, phosphorus carrying the negative charge, arsenic carrying the negative charge, Sb carrying the negative charge. Are these elements belonging to the same period or same group? Well, these are the elements which belong to the same group. And whenever you need to compare the stability of the charges on the elements belonging to the same group, we decide on the basis of volume charge density, right? Now people, among nitrogen, phosphorus, arsenic, antimony, where do you see the size maximum? Antimony has got maximum size. If antimony has got maximum size, it will be having less volume charge density. Lesser the volume charge density, more is going to be the stability. So this is going to be the stability order over here of the charges, right? Number 1. Number 2, oxygen carrying negative charge, sulfur carrying negative charge. These elements, oxygen and sulfur, again they belong to same group, right? Now, whenever you need to compare the stability of the charges on the elements which belong to the same group, which concept? Volume charge density, right? Have a look. Oxygen carrying negative, sulfur carrying negative. Now, can I say sulfur has got more size? If sulfur has got more size, it will be having less volume charge density. Lesser the volume charge density, more is going to be the stability. So this is going to be the stability order of these charges present on these species. As simple as that. Yes, Mahesh, you can watch it for JE too. Perfect. Now we will have a look. This is the carbon carrying positive charge, this carbon carrying positive charge, and this carbon carrying positive charge, right? Now have a look. This is a triple bonded carbon. Over here, this is the double bonded carbon. Over here, this is a single bonded carbon. You guys must be familiar with the fact triple bonded carbon has got the more S character than that of double bonded carbon than that of single bonded carbon. More the S character, more the electronegativity. More the S character, more the electronegativity. And you know, positive charge is more stable on less electronegative element. I must say this carbon is least electronegative among all these carbons carrying positive charge. So this is going to be the stability order, as simple as that, right? Perfect. In the similar way, check the next one. This is the carbon carrying negative, this is the carbon carrying negative, and this is the carbon carrying negative. Again, this is the triple bonded carbon, more S character, more electronegativity, and negative charge is more stable on more electronegative element. So this is going to be the order of the stability of these charges. I'm sure you can easily from now onwards check on which species the charge is more stable and on which species the charge is less stable. Just 2 things which you need to remember. Whenever the elements belong to the same period, you'll be deciding on the basis of electronegativity. Whenever the element belongs to the same group, you'll be deciding on the basis of volume charge density. Lesser the volume charge density, more the stability, right? As simple as that. Perfect. Yes, Srinitya, you can watch it for MCET examination as well. Absolutely, the level is going to be the same. All right, arrange the following arrange the following in the stability order. Arrange the following in the stability order. Now people have a look. This is a 3-membered ring, this is a 4-membered ring, 5-membered ring, 6-membered ring. Well, let me tell you, 3-membered ring will have maximum strain, right? 3-membered ring is under maximum strain. And more the strain, more is going to be electronegativity. You must have studied about that as well. If I ask you, which carbon among these carbons, either this one, let me call this as carbon number 1, let me call this as carbon number 2, let me call this as 3, let me call this as 4. So which carbon is going to be more electronegative among all these 4 carbon atoms? I'll say wherever angle strain is maximum, right, then only the carbon atom will have more electronegativity. So 1 is more electronegative, followed by 2, followed by 3, followed by 4. More the electronegativity, you know, negative charge is more stable on more electronegative element, right? So this is going to be the stability order of these charges, as simple as that. Perfect. If you look at the next one, right, similar sort of question, it is just positive charge in place of negative, right? Positive charge is more stable on less electronegative, so this is going to be the stability order, right? As simple as that. I'm sure you can easily solve these sort of questions from now on. Perfect. Now the similar sort of concept I'm going to use in order to check the acidic strength of different species, right? Well people, in the first question you need to check which among the two is more acidic. Which among the two is more acidic? What you shall be simply doing, you shall be first of all making their conjugate bases. You shall be making their conjugate bases, right? Yes? Now people, just take the H positive out from this acid, it becomes RO negative. Take the H positive out from this particular acid, it becomes RS negative. So you made the conjugate bases. Now check the stability of these conjugate bases, my dear people. Check the stability of these conjugate bases. Right here, oxygen carrying negative, sulfur carrying negative, right? Oxygen and sulfur, they belong to same group. So volume charge density plays a role here. I'll say sulfur has got more size, so less volume charge density, more stability. So this is going to be the stability order of their conjugate bases. And whatever is going to be the stability order of their conjugate bases, same is going to be the order of their acidic strengths. Perfect. So this is going to be the order. Yes, people, simple and basic. Now check the next one. Check the next one, my dear people. Check the next one. Have a look. First of all, you'll be making their conjugate bases. Take H positive out, there will come negative charge on this carbon. Take H positive out from here, negative charge on this nitrogen. H positive out, negative charge on this oxygen. Take H positive out, negative charge on fluorine, right? Now check, after taking H positive out, right? Check the stability of the conjugate bases. I must say, carbon having negative, nitrogen having negative, oxygen having negative, and fluorine having negative. All these elements, carbon, nitrogen, oxygen, and fluorine, they belong to same period. And negative charge is more stable on more electronegative element, right? So I must say, the conjugate base of this HF is more stable, and whatever is going to be the stability order of their conjugate bases, same is going to be the stability, same is going to be the acidic strength order of their corresponding acids. As simple as that, right? Simple and basic. Look at the next one. So take H positive out. If you take H positive out, my dear people, it becomes OH with a negative charge. If you take H positive out from here, it becomes SH with a negative charge. Oxygen carrying negative, sulfur carrying negative. They belong to same group. Volume charge density plays a role. Lesser volume charge density, more stability, right? So this is going to be the stability order of their conjugate bases, and you know, whatever is going to be the stability order of their conjugate bases, same is going to be their acidic strength order. So this is the acidic strength order, as simple as that, right? In the similar way, my dear people, just take H positive out from here, you'll find negative charge on this carbon. Take H positive out from here, you'll find negative charge on this carbon. Take H positive out from here, again you'll see negative charge on this carbon. Well, my dear people, after taking the H positives out, right, check the stability of the conjugate bases. Negative charge is more stable on more electronegative element. This is a triple bonded carbon carrying the negative charge, right? So more electronegative, more S character. Yes, as simple as that. So I must say the conjugate base of this particular acid is more stable. That means its corresponding acid is going to be stronger. So this is going to be the acidic strength order. As simple as that, right? Simple and basic concept which I'm using, which I told you a few minutes back only. A very simple and basic question which I'm sure every one of you can solve, right? Well, my dear people, if you look at all these carbocations are stabilized by hyperconjugation basically. So what do you need to do over here? Just do one thing. Just calculate the alpha hydrogens, right? Calculate the alpha hydrogens. If I ask you, how many alpha hydrogens are here? 0. How many alpha hydrogens are here? 3. How many alpha hydrogens do we have in this particular case? 6. How many alpha hydrogens do we have here? 9. More the alpha hydrogens, more is going to be the hyperconjugation, and more the hyperconjugation, more is going to be the stability. So this is going to be the stability order of these carbocations, as simple as that, right? In the similar way, if you take the next one, every carbon over here is carrying the negative charge, negative, this carbon carrying negative, this carbon carrying negative. Well, is CH3 electron withdrawing or electron donating? It's electron donating, right? You know, electron donating groups, they decrease the stability of the carbanion, right? More electron donating groups, so lesser the stability, right? So what is going to be the stability order? I must say this is going to be the stability order, as simple as that. Perfect. Right, people? I'm sure this is clear to everyone. Arrange the following according to their acidic strength, right? You need to arrange them on the basis of their acidic strength. Again, you are going to follow the same concept. What you need to do is, see, these are the two acids which are given to me. I need to compare their acidic strengths, right? Now, people, what you are going to do exactly, just make their conjugate bases. Take this hydrogen out as H positive. There will be negative charge on this particular oxygen. Take this hydrogen out as H positive. Negative charge on this particular oxygen, right? Perfect. Now, my dear people, check the stability of the conjugate bases. Check the stability of the conjugate bases. Have a look. Fluorine is closer towards this O negative as compared to the second case, right? So, fluorine being electron withdrawing, more the electron withdrawing nature, right? More is going to be the stability of the conjugate base, and more the stability of the conjugate base, more is going to be the acidic strength order, and so this is going to be your order of the acidic strength, as simple as that, right? Perfect. If you look at the next one, my dear people, again the similar sort of concept you'll be using. Take H positive out from here, negative charge over here. Take H positive out from here, negative charge over here. Take H positive out, negative charge. Take H positive out, negative charge. Now, which ring is more electron withdrawing? I must say the first ring is more electron withdrawing. If first ring is more electron withdrawing, it is going to decrease the amount of the intensity of negative charge on this particular oxygen, right? So the conjugate base in the first one is more stable. So same is going to be the acidic strength order of their conjugate acids, as simple as that, right? Perfectly done? Right, people? Absolutely, all of you are perfectly right. Moving on to the next set of questions. Arrange the following on the basis of their basic strengths, right? You're going to arrange them on the basis of their basic strengths. If I ask you about this lone pair and this lone pair, which one is localized and which one is not? Well, first of all, let's leave the localization, delocalization aside. If I ask you, what is the hybridization of this particular nitrogen? This nitrogen is forming 3 sigma bonds and 1 lone pair, so it's sp3 hybridized, right? It's sp3 hybridized. Perfect. What about the hybridization of this particular nitrogen? It's sp2 hybridized, right? sp2 hybridization means more s character as compared to sp3. So this particular nitrogen, it has got more s character, it's more electron negative, right? So availability of this lone pair will be comparatively less as compared to the first one, right? So wherever availability of the lone pair is more, that you know is going to be more basic. So first one absolutely is going to be more basic than that of second one, as simple as that. Perfectly done. If you look at the second one, my dear people, see, again this is your site, again this is your common site. If I ask you, this is chlorine, right? This is fluorine here. Which one is more electron withdrawing? Fluorine absolutely in this particular case is more electron withdrawing. If fluorine is more electron withdrawing, I must say this one is going to be, the second one is going to be less basic as compared to the first one, right? So this is the one. Right, people? Manisha, there is no conjugation. I mean, this lone pair is not participating in the conjugation, right? It is not involved in the conjugation. Okay? Right? Perfect, guys. Look at the next one. Look at the next one. Again, the similar sort of concept. This nitrogen carrying lone pair. This is the one carrying lone pair. This is the one carrying lone pair. This is sp3, less s character, more availability of lone pair, so more basic. So this is going to be the order of the basic strength. As simple as that. Right, people? Okay, correct order of the stability of these resonating structures. So you need to arrange these resonating structures on the basis of their stability order. So how do we check them? How do we check them, people? Check it out. It's again the simpler concept. Have a look. See, first of all. First thing, just count the covalent bonds. 1, 2, 3, 4. 4 covalent bonds here. 1, 2, 3 and 4. 4 covalent bonds here. 1, 2 and 3. 3 covalent bonds here. Perfect. Lesser the covalent bonds, lesser the stability. So I got to know 3 is least stable among all. I got to know 3 is least stable among all. Number 1. Number 2. Now in first and second, which one is more stable? Have a look. Over here we have got nitrogen carrying the positive charge. Again we have got nitrogen carrying the positive charge. Right here carbon is carrying negative. Right here nitrogen is carrying negative. Have I told you a few minutes back? Negative charge is more stable on more electronegative element, right? If negative charge is more stable on more electronegative element, I must say first one will be more stable, followed by second, followed by third. This is going to be the stability order of these resonating structures, as simple as that. Perfectly done, right? Yes, people? Simple and basic. I'm sure you are getting to know the level of your examination. All right, a similar sort of question, my dear people, which you need to answer again. Arrange the following on the basis of their stability order. You need to arrange them on the basis of their stability order. First of all, is there any resonating structure which does not contain, charges on its atoms? Yes, the first one, right? It does not contain charges on the atoms. Wherever there will be no charge on the atoms, that is going to be maximum stable. So one is maximum stable. Perfect. Now, you need to identify among these two. So first of all, I'll be counting again the covalent bonds. Check it out. 1, 2, 3, 4, 5, 6, and 7. So there are 7 covalent bonds present here, right? 1, 2, 3, 4, 5, 6, 7, and 8. 8 covalent bonds. More the covalent bonds, more the stability. So 3 will be more stable, followed by 2. So this is going to be the order, right? So first check the charges. Second, count the covalent bonds, right? After that, you can go for the other rules. I'm sure you are going to easily solve these questions from now on. Which of the following is more stable? Among first and second, which one is more stable, my dear people? Well, first thing, this is the lone pair present on the nitrogen, and over here again the lone pair present on the nitrogen, right? Over here this is lone pair, sigma, pi, right? It is a case of conjugation, linear conjugation this is, right? Linear conjugation. If you look at the second case, my dear people, this lone pair is simultaneously in conjugation with this pi bond. At the same time, the same lone pair is in conjugation with this particular bond, right? So this is the case of cross conjugation, right? And you know, extent of resonance in cross conjugation is less than that of extent of resonance in extended conjugation. And wherever resonance is less, stability is less. So I must say, first one is more stable than that of second, as simple as that. Because in the second one, there's the case of what? Cross conjugation. Perfect. Look at the second case, my dear people. Over here, this is the pi bond. Pi, sigma, pi. Conjugation. Pi, sigma, pi. Conjugation. The same pi bond is in conjugation with this one as well as this one, right? So again, this is the case of cross conjugation. And extent of resonance in cross conjugation is less, right? Extent of resonance in cross conjugation is less as compared to this particular one, because this is pi, this is sigma, pi, sigma, and pi, right? On one side conjugation. Perfect. So which one is going to be more stable? The second one is going to be more stable. Yes? Perfect. Right, people? All right. Arrange the following in the stability order. You need to arrange these structures on the basis of the stability order, right? Let's get to know how to check which one is more stable and which one is less stable. Let's get to know that. Well, the first concept which I'll be using over here, do remember the negative charge carrying capacity of oxygen, is greater than the negative charge carrying capacity of 10 carbon atoms. You can find the difference, right? Negative charge carrying capacity on oxygen is far, far, far greater than that of negative charge carrying capacity of carbon. Perfect. So if you'll see negative charge on oxygen, then in some other case you will see negative charge on carbon. Where do you see negative charge is going to be more stable? It's absolutely more stable where? It's absolutely more stable on oxygen. As simple as that, right? Now we will have a look. So I need to arrange them on the basis of their stability order, right? Arrange the following in the stability order, all right. So first of all, this is negative, this is sigma, this is pi. So there can be the resonance. Due to resonance, the negative charge can come here on this particular carbon. Due to the resonance, the negative charge can come on this particular oxygen. Due to resonance, the negative charge can come on this particular nitrogen. Due to resonance, the negative charge can come on this particular oxygen, right? And due to resonance, the negative charge can come here on this particular carbon, right? Then it can again participate, the negative charge can come here. Then it can again participate, the negative charge can come here, right? So these are the positions wherein you get the negative charge, right? In the similar way, my dear people, this is the negative charge, right? This is the negative charge. It can participate in the resonance, so negative charge can come here. Then in the other case, negative charge can come here. In the other case, negative charge can come here, right? Perfect. These are all the possibilities which I've shown you, right? Now have a look. There is only one structure, my dear people. There is only one molecule among all, wherein, due to resonance, negative charge is shared by 2 oxygen atoms. That is here. Negative charge is shared by 2 oxygen atoms. You know, negative charge carrying capacity of oxygen is far, far ahead than that of what? Far, far ahead than that of carbon. Perfect. And there are 2 oxygen atoms which share the negative charge. So I must say D is going to be maximum stable among all. D is going to be maximum stable among all, right? Perfect. So leave this case aside. Now find the other molecules wherein you find the oxygen atoms. Oxygen is present here, oxygen is present here. Due to resonance, oxygen is carrying negative charge. Due to resonance, oxygen is carrying negative charge here, right? So you are not going to decide on the basis of oxygen in these 2 molecules. You're not going to decide on the basis of the oxygen over here, right? You'll be deciding on the basis of number of resonating structures. I must say E will have more resonating structures than that of B. So E is absolutely going to be more stable than that of B, right? So this one is done and dusted. Even this one is done and dusted, right? Now, my dear people, among A, C and F, right? If you look at this particular structure, you have got nitrogen carrying the negative charge, nitrogen being more electronegative, negative charge or more electronegative element is more stable. So C is going to be more stable, right? Now among A and F, right? Look at A and F, my dear people. Over here, there'll be more resonating structures. More resonating structures means more stability. So F will be more stable than that of A, right? So this is going to be your stability order, which you were supposed to check in this particular question. I'm sure this is clear to every one of you. You can quickly let me know in the chats if everything seems clear to you. Quickly let me know in the chats, my dear people, if every single thing seems clear to you. And if you're not liked the video yet, please do like the video, share the video with all of your friends, and do subscribe to the channel as well, right? Yes, perfectly done. Let's move on to one more type of the question which can be asked. Arrange the following on the basis of their bond lengths, right? So this is the bond length. This is again second bond length, third bond length, and fourth bond length. You need to arrange them on the basis of their bond lengths, right? Well, people, I must say this is a pure single bond between nitrogen and carbon. This is a pure double bond between nitrogen and carbon. Due to resonance, my dear people, there will be partial double bond character over here. Due to resonance, again, there will be partial double bond character over here, right? So I must say 2 is the only one which carries the pure double bond. So the bond length over here between nitrogen and oxygen is going to be the minimum. The bond length is minimum in 2. The bond length is minimum in 2. And bond length is maximum in 1 because it's a pure single bond. It's a pure single bond, right? It's a pure single bond. Now among 3 and 4. In 3 and 4, due to resonance, this particular nitrogen and carbon, right, they are getting the partial double bond. Even due to the resonance, in the last case, this particular nitrogen and carbon, they are again getting the partial double bond. Now, where is the resonance more among 3 and 4? The resonance is more over here, right? You can check lone pair, sigma, pi, right? Resonance is more in the fourth case. If resonance is more in the fourth case, I must say this bond will get more double bond character. More the double bond character, less the bond length. So 4 will have less bond length as compared to 3, right? 4 will have less bond length as compared to 3. Perfect. So this is going to be the order of the bond lengths which you were supposed to check among all, right? Perfectly done. Yes, people. Moving on to one more. Arrange the following on the basis of their Ka values, right? Well, Ka basically decides the acidic strength, right? More the value of Ka means, more is going to be the acidic strength of the molecule, as simple as that. Now, my dear people, you need to arrange them on the basis of their, acidic strengths. First of all, what I would suggest you guys, just select the reference which is common in every molecule. This is the reference which is common in every molecule from where hydrogen is going to go as H positive, right? Now, people, you know, acidic strength, it is directly proportional to minus effect, and you know, minus M dominates over minus H, and minus H dominates over minus I. This is the simple concept which you guys will be using over here in this particular case, right? Now, we will have a look. Over here, there is a nitro. This is the nitro which is attached. Perfect. So it will absolutely show minus M, right? This is Cn. It is again going to show minus M, right? This is F. F is going to show plus M and minus I, right? This Cl is going to show plus M and minus I, right? So first thing, Nitro has got the more minus m power than that of CN. So I must say 1 will be maximum acidic followed by 2. Now among 3 and 4, right? This is parafluorophenol. This is parachlorophenol. Do remember both these F and Cl, they show plus M and minus I. Plus M and minus I, right? But do remember chlorine in case of parachlorophenol, it shows more electron withdrawing nature than that of this fluorine in parachlorophenol. That is the reason why this parachlorophenol is going to be more acidic than that of parafluorophenol. So this is your actual acidic strength order. So do remember it from now onwards. Do not write it as 1, 2, 3, 4. Write it as 1, 2, 4, 3. Right? Perfect. Do remember it from now on. I'm sure everything is clear till here. So we will, one more, arrange the following on the basis of the Kb, right? So you know, more the value of Kb, you know it, more the value of Kb, more is the basic strength, right? See, if you look at the first molecule, there's a very common molecule which is what we call as guanidine. That is maximum basic, you know it already, right? So 1, I'm not going to check, 1 is maximum basic among all, right? Now in the rest of the 3, I'm going to select the common thing. This is the common thing, our reference part. This is the common thing. Now this OH over here is going to show plus M effect from here, my dear people. The CH3 is going to show plus H and CN is going to show minus M over here, right? Now you know basic strength is directly proportional to plus effects, and you know plus M dominates over everything, followed by plus H, followed by plus I, right? This is something which you guys are going to remember. As simple as that, right? Yes? Right, people? Now have a look exactly. 2, 3 and 4. 2, 3 and 4. This is showing plus M, right? Plus M dominates over everything. So absolutely after 1, second is going to be more basic. Now among 3 and 4, plus H, this showed minus M, right? So 3 is going to be more basic than that of 4. So 1, 2, 3, 4 is again the order over here, right? Well, Harshit, you can watch this session for the EAM CET examination as well. No issues, right? Because the level is going to be similar. Alright, arrange the following on the basis of their Kb value. Again, you need to arrange them on the basis of their basic strength, right? And I told you a few minutes back only, basic strength is basically directly proportional to plus effect. And you know, plus M, it dominates over plus H, and plus H dominates over plus I, right? That's all which you need to take into consideration. Rest you can solve the equation on your own. So first thing which I'll be doing, I'll be selecting the reference which is common everywhere, right? This is the reference which is common everywhere, right? Number 1. Number 2, this is CH3 attached at the para position, so it's going to operate plus H effect. This is CX3, CCl3, it's going to operate minus H. This is CH3 at the meta position, so it's going to operate plus I, right? And this is CL3 at the CCl3 at the meta position, so it's going to operate minus I from here. Perfect. Now guys, select it. See, this is the only one which is showing plus H effect. Plus H dominates over plus I, right? So first one is going to be maximum basic among all. Right? Yes, as simple as that. Now look at this one. This is going to be CH3, right? This is going to be CH3. It's showing plus H effect. So third is going to be given the second priority. Now among 2 and 4, which one is going to be more basic? Among 2 and 4, which one is going to be more basic? Can you let me know fast? Among 2 and 4, which one is going to be more basic? Fast. This is minus H. This is minus I, my dear people, right? So you'll be giving the priority to fourth, and at the end you'll be giving priority to second. So this is the order. 1, 3, 4, 2. Yes? Perfect, people? Simple. Now moving on to one more. Arrange the following on the basis of K. Again the acidic strength order. So first of all, I'll be selecting the reference which is common everywhere. This is the reference which is common everywhere, number 1, right? Now you know, acidic strength is directly proportional to what? Minus effects, and minus M dominates over minus H, and minus H dominates over minus I. You know it? Perfect. Now, have a look. The CH3 over here, it's going to show plus H effect from here, from the para position. The CH3 is present at the meta, so it's going to show plus I effect, right? The CCl3, which is present at the para position, so it's going to show minus hyperconjugation. CBr3, again CX3 form, so minus H. CCl3 at the para, so it's going to show minus I effect, right? So you identified the effects over here. After the identification of the effects, you're done with the question, right? This is showing plus H, this is showing plus I. So first priority shall be, wait, I'm going to write the K order. All right, this is the K order, acidic strength order, right? Acidic strength order. Is anyone showing minus I? No one is showing minus I. Is anyone showing minus H? Yes, these two are showing minus H, but let me tell you, minus H of this CBr3 will be more than that of minus H of this CCl3. So fourth one is more acidic, followed by third one. So these two are gone, done and dusted. Now this is showing minus, so you'll be giving priority to 5. Now among first and second, which one is going to be more acidic? Plus H or plus I? Plus I will be more acidic than plus H. So second, then that of, then at the end, first. So this is going to be the step, this is going to be the acidic strength order among all, right? Perfect, guys. Simple and basic again. All right. Let's have certain questions from the aromaticity, right? You need to identify which molecule is aromatic and which molecule is non-aromatic, right? Well, we will in this particular case, it is cyclic. There is complete cyclic conjugation. It is planar as well because every carbon in the ring is sp2 hybridized, right? And check how many electrons are how many pi electrons are involved in the complete cyclic conjugation. 2, 4, 6. So 6 pi electrons are involved in the complete cyclic conjugation. So it's following the Huckel's rule. It's going to be aromatic, right? Yes. Now check this one. 2, 4, 6, 8, 10, 12, 14. Is it following 4n plus 2 pi? Yes, it's following 4n plus 2 pi. There are 14 pi electrons involved in the complete cyclic conjugation. It's following the Huckel's rule, so it's supposed to be aromatic, right? What about the next one? Check it out. 2, 4, 6, 8, 10. Again Huckel's rule, right? So it's going to be aromatic. So all these three compounds over here are aromatic, right? All these three are aromatic. Now check these, my dear people. Which of the following is aromatic and which of the following is non-aromatic, right? Now first of all, if you want to check whether this molecule is aromatic or not, first thing, just check whether the molecule is cyclic. Yes, it is cyclic. Number one, it is cyclic. Number two, is it planar? See, this sp2, this sp2 planar, sp2 planar, sp2 planar. So this has to be sp2, then only the molecule overall is going to be planar. Let me tell you, this sulfur has got two lone pairs, out of which one is involved in the conjugation. So you are not going to count this lone pair for the hybridization purpose. So it is forming 2 sigma and 1 lone pair. This is again sp2. If this is sp2, it's going to be planar only. So the molecule overall is planar, right? Now check how many pi electrons are involved in the complete cyclic conjugation. 2, 4 and 6. So 6 pi electrons are involved in the complete cyclic conjugation. That's why it's going to be aromatic again, right, people? Now if you look at this particular lone pair, again it is participating in the resonance. Again, it's involved in the conjugation, so you are not going to count this lone pair for hybridization purpose. So 1, 2 and 3, only 3 sigma bonds, so this sp2, so the molecule overall is planar, right? Now check 2, 4, 6, 8 and 10 pi electrons involved in the complete cyclic conjugation, so this is supposed to be aromatic, right? If you look at this particular carbon, my dear people, it's sp3 hybridized. If it is sp3, the molecule overall is non-planar. If it is non-planar molecules are neither aromatic nor anti-aromatic. That's why it is non-aromatic, right? And look at the last case, my dear people. See, if you look at this particular bond, there'll be 2 hydrogens attached like this, right? So this again sp3 hybridized. sp3 means non-planar, non-planar means non-aromatic, right? So that's what we were supposed to check, right? Now among these, identify aromatic, anti-aromatic and non-aromatic. See, first of all, this ring is aromatic, this ring is non-aromatic. Let me tell you, aromatic plus non-aromatic makes the overall molecule aromatic. Aromatic plus non-aromatic makes the overall molecule as aromatic, as simple as that. This ring is aromatic, this ring is aromatic. Aromatic plus aromatic makes the overall molecule aromatic. The overall molecule is aromatic. Now let's have a look on the next case. Well, in order to make you understand the next case, let me draw its structure like this. It is one of the same only. These are the 2 same molecules, right? Now we will have a look. If you look at this particular ring, 6 pi electrons involved in the complete cyclic conjugation. If you look at this particular ring, 2, 4 pi electrons involved in the complete cyclic conjugation, right? So the first one is aromatic, the second one is anti-aromatic, and aromatic plus anti-aromatic makes it anti-aromatic. So the overall molecule is anti-aromatic here, right? As simple as that. Perfecto? Yes? Okay, the last one. Look at this particular carbon, my dear people. Look at this particular carbon. There will be 2 hydrogens attached with this one, right? So this is sp3 hybridized. This is non-planar. If it's non-planar, it's going to be what? It's going to be non-aromatic. So this is the non-aromatic molecule. That's all. Perfecto. So let's have a look on chemical kinetics now. These were the questions which were from the general organic chemistry. Now, do you want to do the chemical kinetics first or you want to do the electrochemistry first? Right? The ball lies in your court. Just tell me in the chats. I'm going to start with that chapter. Chemical kinetics or electrochemistry? Till then, I can have some water. Let me know fast. Which one, guys? Do you want me to start with chemical kinetics or electrochemistry now? I can see majority of the students are coming up with kinetics. Now people have started writing electro, but still some people are saying kinetics. I think kinetics is your favorite, is that? Is it that simple? Is it that simple, my dear people? I did not know that it's this much simple. Alright, first we'll do kinetics, then we'll do the electrochemistry, right? But I would want you guys to be with me till the end, yeah? And the ones who have not liked the video yet, please do like the video and share it with everyone. Whosoever is preparing for the NEET 2022, do share it. Let everyone get benefited out of these sessions. Perfect? Alright, so let's see exactly. And by the way, my dear people, I forgot to tell you, tomorrow we are going to have the formula revision. Tomorrow we shall be having the formula revision, okay? Whatever formulas are there in the chemistry, right? All those formulas I'll be giving you in a single session, which is just going to be 1 hour long. And everything is going to be handwritten, right? Because from your physical chemistry, I can say majority of the questions which you get in your NEET examination or even JEE Mains examination, majority of the questions will be formula based only, right? There'll be a simple concept involved and then you will have to apply the formula, right? And later on, you will have to solve the equation. Perfect. So tomorrow, do join me. I'll be coming up with a formula revision session at sharp 9 p.m. Perfect. Let's get going with the concepts of the chemical kinetics in the form of questions, right? So the timing for the session is going to be 9 p.m., not a.m. It's p.m. Perfect. Now we will have a look. One of the simple questions from which I'm starting with, right? You are given with a reaction which is balanced. This is a balanced chemical equation, right? This is a balanced chemical equation. The stoichiometric coefficient right here is 1. The stoichiometric coefficient right here is 1. The stoichiometric coefficient right here is 1/2. Perfecto. I would want you guys to write the rate of the reaction in terms of H2O2. Since H2O2 is the reactant, so you'll be starting with a minus sign. 1 divided by stoichiometric coefficient of H2O2 is 1. Change in the concentration of H2O2 divided by time interval dt. This is the first way by means of which you can calculate rate of the reaction in terms of H2O2. In the similar way, I would want you guys to write the rate of the reaction in terms of water as well. Since water is your product, you will be starting with the positive sign. 1 divided by stoichiometric coefficient is 1. It is change in the concentration of H2O divided by time interval, that's dt, is equal. O2 is again the product. I'll be starting with the positive sign, right? 1 by stoichiometric coefficient. 1 by 1/2 comes out to be 2. Change in the concentration of O2 divided by dt, right? Now people, how do I solve this particular equation? Have a look. It's simple. It is simple. If the concentration of H2O2 changes from 0.5 to 0.05. If the concentration of H2O2 changes from 0.5 to 0.05. So this is the initial concentration of H2O2 and this is the final concentration of H2O2, right? And this is the time interval which is given to us. We need to calculate rate of the reaction. So rate of the reaction can be calculated by solving this particular term. I can say rate of the reaction over here is going to be minus change in the concentration of H2O2, which is final concentration minus initial. Final is simple, that is 0.05. Initial is 0.5 divided by time interval, that's 15 seconds. You need to solve this term and get the answer in moles, liter inverse, second inverse. This is the first part of the question, which is done and dusted, right? Which is done and dusted. Yes? Number 1. Number 2, you need to calculate the rate of appearance of O2. How do we write the rate of appearance of O2 mathematically? If I talk about the rate of appearance of O2, rate of appearance of O2 will be started with the plus sign. Then I'll be writing change in the concentration of O2 divided by dt without dividing with the stoichiometric coefficient. This is something which I call as the rate of appearance of O2. Rate of appearance of O2, whose value you are supposed to calculate. So the value of this particular term, you need to calculate. So what I'll be doing? From this particular equation, I'll be taking this term. I'll be taking this term and I shall be taking this term as well. Just equate the two terminologies. If I equate the two terminologies, I'll write something like this: d of O2 divided by dt should be equal. Take this 2, make it as the denominator over here. It's going to be minus 1 divided by 2. Change in the concentration of H2O2. Final concentration of H2O2 minus initial concentration of H2O2 divided by time interval 15 seconds. Just solve it and get the answer in moles, liter inverse, second inverse. What do we call this term? Do we call this as the rate of appearance of O2? Absolutely. After solving this particular term, you'll be getting the rate of appearance of O2, my dear people, right? Clear to everyone? Yes? Well, Jyoti, I have already taken a session on hybridization and everything. You can just search it out. Hybridization by Wasim sir, you'll be getting a lecture on that. From that particular topic, you'll get to know how to calculate the hybridizations and everything, right? Moving on, my dear people. Yes, Naveen, I'll be getting back to you at the end of the session. If the rate of appearance of O2, how do I represent mathematically? Rate of appearance of O2 is represented like this. This is rate of appearance of O2. That's given to me as 0.5 moles, liter inverse, second inverse. Then calculate the rate of disappearance of N2O5. How do I write disappearance of N2O5? Minus d of N2O5 divided by dt. This is something which I call as rate of disappearance of N2O5, and its value I need to calculate, right? So what is the first thing which I'll be doing? I'll be writing the differential form of rate for this particular reaction. I'll say rate of reaction in terms of N2O5. Since it's a reactant, I'll be starting with minus sign. 1 divided by stoichiometric coefficient is 2. It's going to be change in the concentration of N2O5 divided by dt is equal. In terms of N2O4, it's going to be plus 1 divided by 2. Change in the concentration of N2O4 divided by dt. In terms of O2, my dear people, it's going to be plus change in the concentration of O2 divided by dt, right? As simple as that. Now have a look exactly which all terms I'll be taking from this particular equation. See, first of all, I'll be taking this particular term from the equation, and at the same time, I'll be taking this particular term from the equation. I'll just equate the two. When I equate the two, I'll write it as minus d of N2O5 divided by dt. I'll take this 2 from here and make it the numerator over here. So it's going to be plus times 2 multiplied by d of O2 divided by dt. And my dear people, you know d of O2 divided by dt is given to you as 0.5. So multiply it with 0.5. The value comes out to be 1 moles liter inverse, second inverse. This is the rate of disappearance of N2O5 which you were supposed to calculate as far as the question was concerned, right? Wasn't it simple, my dear people? Wasn't it simple? Yes? All right, one more. Simple and basic question. For a chemical reaction, A gives B. What just happened? Just a second, guys. See, guys. We are given with a reaction A gives B, right? This is the reaction which we are given with, whose rate constant is given to us as K, right? The first thing which I'll be doing, I'll be writing the rate law for this particular reaction. I'll say rate law is equal to rate constant, rate of reaction is equal to rate constant multiplied by concentration of A raised per X. This X is something which we call as order of the reaction with respect to A, and at the same time, this X is called as the overall order of the reaction as well, right? Now, my dear people, have a look. Let me call this as equation number 1. It is a simpler one. It is found that the rate doubles. So initially the rate was R, now it becomes 2R. The rate doubles when the concentration of A is increased 4 times. So initially it was A, now it's going to be 4 times A. So when the concentration of A is increased 4 times, the rate of reaction doubles. What is going to be the rate of the reaction, right? What is going to be the rate of the reaction? What do you need to do? Just divide the two particular equations as 2 divided by 1. Well, after dividing second by first, this RR gets cancelled out. So on the left hand side, you'll be getting 2. K gets cancelled, A raised per X cancelled. So it's going to be 4 raised per X over here. So what should be the power of 4 such that 4 raised per power is equal to 2. So I must say X should be equal to 1 by 2. And what was this X, my dear people? This X is nothing. This X is going to be the order of the reaction with respect to A, or you can call this as overall order of the reaction as well. So you got to know the order of the reaction over here is equal to 1 by 2. Perfectly done, right? Now people, let me move on to one more question. This is one more type of the question which is asked from the chapter Chemical Kinetics. Let's have a look how to solve this particular question. Well, this is the reaction that's given to me. So first of all, what do I do over here? I'll be writing the rate law. If I write the rate law, it's going to be rate constant, concentration of NO raised per X, concentration of NO raised per X multiplied by concentration of H2 raised per Y. This is your rate law first of all, yeah? This is your rate law. Well, after writing the rate law, what I would suggest you guys to do over here, see, if you look at the experiment number 1 and experiment number 2, right? Look at the two experiments carefully, right? In the first two experiments, I'm keeping the concentration of H2 same. I'm keeping the concentration of H2 same in the first two reactions. So imagine there is no H2 over here, right? And in the first two experiments only, are we increasing the concentration of NO? Absolutely. We are increasing the concentration of NO 3 times. And on increasing the concentration of NO 3 times, what is happening to the rate of the reaction? 3,9. So it is increasing 3 times. As simple as that, right? So if I just omit this H2 over here in the first two experiments, on increasing the concentration of NO 3 times, rate is becoming 9 times. Sorry, rate is becoming 3 times. So making this 3 times, rate is becoming 3 times. So this X has to be 1. This X has to be simply 1. Perfect. Now, my dear people, if you look at experiment number 2 and experiment number 3, the concentration of NO is kept fixed. In 2 and 3, NO concentration is kept fixed. So imagine as if there is nothing over here, right? Now check. The concentration of H2 is increased 4 times, and on increasing the concentration of H2 4 times, rate of the reaction is increased 4 times as well. Check it out, right? So on increasing the concentration of H2 4 times, rate is becoming 4 times, right? So Y actually has to be 1 over here, right? Then only these experiments are going to be, right, valid. Perfect. So one is called as the order with respect to NO. This one is called as order with respect to H2. If I ask you what is the overall order of the reaction, you must say overall order of the reaction is 1 plus 1. That comes out to be 2. So overall order of the reaction over here is going to be 2. Perfect, people. Is it clear to everyone? Let me quickly know in the chats. Let me quickly know in the chats if everything seems clear to you fast. Yes? All right. Let's have a look on one more. The question based on the zero order reaction, right? The question based on the zero order reaction. How do we solve this particular question? Well, my dear people, a zero order reaction is 20% completed in 10 minutes. At what time it will be 80% completed, right? It is again a simple question. See, in 10 minutes, a zero order reaction is 20% completed. Perfect. So in 20 minutes, a zero order reaction will be 40% completed, right? Yes? Right, people? So in 30 minutes, a zero order reaction will be 60% completed. So in 40 minutes, a zero order reaction will be 80% completed. So what is the answer of the question? Right? Right, people? Sai Varun, did you get 0 percentile or 100 percentile? Right? Guys, this is the one way of solving the equation, right? The other way of solving the equation, let's have a look on that. Let's have a look at that. So first of all, I've got a reaction as A gives B, for example, whose rate constant is K, and I'm assuming the order of the reaction is 0. It's a zero order reaction, right? It's a zero order reaction, number 1. Let's assume at time t is equal to 0, the concentration of reactant is A0, and this is going to be 0, for example, right? At time t is equal to 0. Perfect. Well, people, after 10 minutes, it's observed that 20% of the reaction is complete. That means 20% reactant has converted into product. If 20% of the reactant has got converted into product, so I must say 80% of the reactant will be still left in the container, and 80% of the reactant is going to be 0.8 A0. This is going to be the concentration of reactant after 10 minutes. This is going to be the concentration of reactant left after 10 minutes. What do we need to calculate? At what time the reaction will be 80% completed? At what time the reaction will be 80% completed? What is meant by 80% completion? It means 80% of the reactant is getting converted into products. If 80% of the reactant is getting converted into products, I must say 20% of the reactant will be still left in the container as such, right? So I basically got two conditions. At time t is equal to 10 minutes, the concentration of reactant left is 0.8 A0. At time t, the concentration of reactant left is 0.2 A0. And I need to get the value of t. That's what we need to do, right? That's what we need to do, my dear people. Now, first of all, I'll be using the integrate rate equation for the zero order kinetics. You know, for the zero order kinetics, AT is equal to A0 minus KT. This is the integrate rate equation which every one of you must be knowing. Now, in this particular integrate rate equation, I'll be using this condition and this condition. If I use the first condition, AT in the first condition is nothing, that is 0.8 A0 is equal to A0 minus K. What is the value of T in the first condition? It's 10, right? So from here, I would want you guys to get the value of K over here. It's going to be equal to 0.2 A naught divided by 10. This is the value of K which you got over here, right? It's going to be moles, liter inverse, minute inverse. Perfect. This is the rate constant which I calculated. Now, after calculating the rate constant, I would want you guys to use the second parameter into this particular equation. Now, if I use the second parameter into the zero order kinetics equation, I must say AT in the second condition is 0.2 A naught is equal to A naught minus, what is the value of K? K value is nothing, it is 0.2 A naught divided by 10 multiplied by T. So this A naught gets cancelled out. After solving this particular equation, you'll get the T value over here as 40 minutes. So you must say after 40 minutes, 80% of the reaction would have got completed, my dear people, right? Simple and basic, which you can solve with this approach as well, right? Perfecto. So moving on to one more question, my dear people. T half for a zero order reaction. So half-life of the zero order reaction first of all is given. Half-life for the zero order reaction is given to be as 1 hour. If half-life is given, you know, half-life is nothing, that is A naught divided by 2K, right? That's equal to 1 hour as far as the equation is concerned. Well, the initial concentration is given to be as 1 molar divided by 2. I'm sorry, the initial concentration of the reactant is not 1 molar, it's 2 molar, right? The initial concentration of reactant is 2 molar, that means A naught is 2 molar, divided by 2 is equal to K. So K value over here I got to know as 1. K value I got to know over here as 1, right? And its units are absolutely going to be moles, liter inverse, R inverse. This is the value of rate constant which I got. So first condition I used to calculate the rate constant of the zero order reaction, number 1. Number 2, how much time does it take for the concentration to reduce from 0.5 to 0.25? Now, in the second condition, let me call this as A naught, let me call this as AT. And the time in which, right, the time in which the concentration of reactant reaches from 0.5 to 0.2, let me call that time duration as T. Perfect. Now I'll be again using the integrate rate equation for the zero order kinetics. It's AT is equal to A naught minus KT. I'll be taking the AT value over here as 0.25 is equal to A naught value as 0.5 minus K value. K is 1 and this is going to be T. So from this T over here, you got the value over here as 0.25 hours. So in 0.25 hours, you'll see the concentration of reactant reducing from 0.5 to 0.25. Is that clear to everyone? Yes? Simple and basic. The first condition I used and got the value of rate constant. The second condition I used, got the value of time. That's all. Yeah? This is one of the approach of solving the equation. You can solve the question with a different approach as well. The choice is all yours. Well, people, if you look at this particular equation, it's a very simple one. I would want you guys to remember certain relations related to the first order kinetics. Do remember, time taken to complete 75% of the first order reaction is nothing else 2 times the half-life, number 1. Number 2, time taken to complete 87.5% of the first order reaction is nothing, that is 3 times the half-life. And at the same time, my dear people, time taken to complete 99.9% of the first order reaction, it's equal to 10 times the half-life, right? These are the 3 relations which I would want you guys to remember, yes, related to the first order kinetics, right? Alright, the equation is simple and basic. The first order reaction is 75% completed. Well, people, 75% of the first order reaction is completed in 100 minutes. So T75 is 100. This is 2 multiplied by T half. So from this particular equation, you are getting T half value over here is 50 minutes. So this is the half-life of the reaction, number 1. What was I supposed to calculate? Time taken to complete 87.5. So time taken to complete 87.5% of the reaction is 3 multiplied by half-life. So the value comes out to be 150 minutes. So 150 minutes is going to be the answer of the equation. That's all, right? Simple and basics, right? Perfect, people. I'm sure you can solve this sort of equation from now on easily with the same approach as I'm showing to you. All right, for the first order reaction, choose the correct value of T half. Well, people, well, the reaction that's given to us, that follows the first order kinetics, right? Number 1. So this graph is valid for the first order reaction. Well, I'm sure you would have made the curve between log of AT versus T, right, for the first order kinetics. And let me tell you, slope of this curve, slope of log of AT versus T, slope of log of AT versus T is equal to how much that is? You know, Log of AT is equal to log of A naught minus K divided by 2.303. So slope is equal to minus K divided by 2.303. Right? And slope is basically tan of theta. Right? What is theta over here? Theta is the angle. Theta is the angle which the curve makes with the positive x-axis in the anti-clockwise direction. So this is theta, which is 135. So this is basically your tan of 135, which is equal to minus K divided by 2.303, my dear people. So this tan of 135 is nothing, it's minus 1. Minus 1 is equal to minus K upon 2.303. So from this particular equation, you can get the value of K, which is going to be 2.303 minute inverse. So this is the value of rate constant which you got. But was I supposed to calculate the rate constant? No way. I was supposed to calculate the half-life of the first order kinetics. You know, half-life of the first order kinetics is equal to 0.693 divided by K. Since K value you have calculated, so T half over here, you'll be getting as 0.693 divided by 2.303, and the value when you solve it, it's going to be 0.3 minutes, right? So this is basically going to be the half-life of the reaction which you were supposed to calculate as far as the question was concerned, right? Perfect. So my dear people, let's move on to one more question then. What amount of reactant for the first order reaction will be left after 3.5 minutes? Take ln 2 is equal to 0.7. This question is incomplete first of all, so let me complete the question. This question is incomplete, let me complete this particular question. The question is like this, there is a graph given with the question as well, and the graph given is between, the graph should be ln of 80 versus T, right? And this is the graph which is given, and this angle is given, this is 45 degree, right? Now the question is complete. Right? Perfect. Let's see exactly how to tackle this particular question. What amount of reactant for the first order reaction will be left after 3.5 minutes? So after 3.5 minutes, what is going to be the amount? What is going to be the concentration of reactant left? Perfect. I'm sure you must have heard about this particular expression. AT is equal to A naught divided by 2 raised power n. This is one of the expressions which you even use in your radioactivity in physics, right? Because radioactivity follows the first order kinetics, and you use this particular expression there as well, right? So AT is the concentration of reactant left after time t, and time t over here is 3.5 minutes, is equal to A naught by 2 raised power n. What is n over here? N stands for the number of half-lives. N stands for the number of half-lives. And number of half-lives is equal to total time divided by T half. Total time divided by T half. Total time is given to me as 3.5 minutes. Now first thing which I need to do, I need to calculate the half-life, right? Now the point is, how do I calculate the half-life? Since the reaction is the first order, so it's 0.693 divided by K. Or let me use the ln term, it's going to be ln of 2 divided by K. Perfect. Now I do not know the value of K as well, so I will have to do something and get the value of K, right? And how do I get the value of K over here, my dear people? How do I get the value of K? From this particular expression, ln of AT versus T. What about the slope of this particular curve? Slope of this particular curve, it's equal to minus K. If this is 45, this is 45, this is supposed to be 135. So tan of 135 is nothing, that's minus 1. So minus 1 is equal to minus K. So K is going to be 1. I'm assuming time is in minutes, right? Yes. 1 minute inverse, right? Since you got the value of K, ln 2, take as 0.7. 0.7 divided by 1 comes out to be 0.7 only. So this is the half-life. Once you get the half-life, so divide it over here, use the value of half-life, the value comes out to be 5. So you are basically supposed to calculate the amount of reactant left after 5 half-lives basically, right? So I must say the amount of reactant left after 5 half-life is going to be A naught divided by 2 raised power 5, which makes it A naught divided by 2 raised power 32. So this is basically the concentration of reactant left after 3.5 minutes, my dear people, or you can say that is the concentration of reactant left after 5 half-lives. Simple and basic. Perfect? Perfect, guys? Alright, one more similar sort of question. Let's try to solve this particular question as well. Well, my dear people, in this particular question, let's see what is asked and what is given. The rate of the first order reaction is 0.04 moles per liter per second at 10 minutes, 0.03 moles per liter at 20 minutes after initiation. Find the half-life of the reaction, right? I'm just going to give you one expression. Do remember that expression from now on and solve these sort of questions easily in lesser time. Otherwise, it's going to take some time. See guys, I'm going to give you 2 expressions. Let's say the reaction is A gives B. I'm assuming its rate constant is K, and at the same time, I'm assuming the reaction follows the first order kinetics. Let's see what is given. Now, my dear people, let's assume at time t is equal to 0, the reactant concentration is A0. This is absolutely going to be 0, right? Let's assume at time T1, the concentration of reactant left is AT1. And when the concentration of reactant left is AT1, let me assume rate of the reaction at that point of time was R1, right? Similarly, at time T2, let's assume the concentration of reactant left is AT2, right? And when the concentration of reactant left is AT2, let's assume rate of the reaction at that point of time is equal to R2. Perfect. Now, one simple expression which is valid for the first order kinetics, do remember it from now onwards. See guys, it's going to be rate constant is equal to 2.303 divided by T2 minus T1. It's going to be log of AT1 divided by AT2. AT1 divided by AT2. This is the first expression which you can use. Or you can use like this, 2.303 divided by T2 minus T1. It's going to be log of R1 divided by R2. These are the two expressions which you can remember directly and solve the question in lesser time. Right? Yes? Well, my dear people, I'll be using the second expression because I'm given with the data of the rates of the reactions at two different times. It is 2.303 divided by T2 minus T1. Well, T2 is given to me as 20 minutes. T1 is given to me as 10 minutes. So 20 minus 10 comes out to be 10, right? It is going to be then log of R1. R1 is 0.04. R2 is 0.03. So 0.04 divided by 0.03 makes it 4 by 3, which is log 4 minus log 3, right? Which is log 4 minus log of 3. Yes, log 4 is nothing, that is 0.6. Log 3 is 0.47. The value comes out to be how much? Just calculate it afterwards. You'll be getting the rate constant from here. And once you get the rate constant, you are supposed to calculate the half-life. And half-life of the reaction is nothing, that is 0.693 divided by K. K you'll be calculating from here by solving this particular one. Put the value of K over here and you get the half-life of the reaction. That's solved, right? Do remember these two equations. You can use these equations if you get this sort of equation in the examination, right? And I would definitely want you guys to remember them. Anyways, moving on. Calculate the activation energy of the reaction. Calculate the activation energy of the reaction. Well, people, I'm sure you would have studied the Arrhenius equation, right? What is the Arrhenius equation all about? Yeah? Let me have some water first. Jan is asking, sir, I'm depressed, confused, damn bored, exhausted. Bro, it looks a story to me. What to do for 5 days? What can you do for 5 days? Whatever you've studied till now, just revise the same things again. Number one. Number two, solve as many mock tests as you can. As many mock tests as you can. Do not study something new right now. It's going to kill your brain, right? Do not do that at all. That is the only suggestion which I would give you, right? And do not think of the consequences. Just put everything into your preparation for these 5 days. I mean, you should not come up with something after the examination that if I could have prepared, I would have scored this much. No, that should not be there. Perfect. So do not think of the consequences. Let's think of the consequences after the examination. Just put our best in the preparation phase, right? There should be no regret afterwards that I should have done that, this, right? Okay, I'm sure that will help out. All right, people, let's move on to this particular question. Well, you know, as far as the Arrhenius equation is concerned, rate constant K. Rate constant K is nothing. It is A e raised to the power minus A divided by RT. This is the equation which every one of you would have studied. This is what we call as the Arrhenius equation, number one. Well, if I multiply this particular equation with ln, I must say ln of K is equal to ln of A minus EA divided by RT. Perfect. Or people, I can convert the same equation into the logarithmic form as well. So it's going to be log of K is equal to log of A minus EA divided by 2.303. This is R and this is 1 by T. Perfect. Now this is the curve which is basically given between log of K versus 1 by T, right? Log of K I'm plotting along y-axis, 1 by T I'm plotting along x-axis. So this whole value becomes M, right? There is a sign minus over here. This becomes C. Y is equal to minus mx plus C. It's a straight line with a negative slope. What about the slope of this particular curve? Slope of this particular curve is minus A divided by 2.303 R, right? Well, you got to know slope of log of K versus 1 by T. Slope of log of K versus 1 by T. is nothing, it is just minus EA divided by 2.303 R. If I ask you the curve that's given to us, what about the slope of that curve? Well, people, theta is given to me as tan inverse. If theta is tan inverse, what does that mean? What does that mean? What does that mean? If theta is tan inverse minus 3, that means tan of theta is equal to minus 3, right? If tan of theta is equal to minus 3, that actually means slope is equal to minus 3. So slope is basically given to me as minus 3, which is equal to minus A divided by 2.303 R. And from this particular equation, I would want you to get the value of EA. I must say, EA is nothing. EA simply is equal to, this is going to be 2.303 multiplied by 3 multiplied by R. This is the value of EA activation energy which you got, right? Now, as for the question is concerned, calculate the activation energy in kilojoules per mole. So I would want you, if in order to solve the first question, I would want you to take the value of R as 8.314. So it's simply going to be 2.303 multiplied by 3. R value you'll be taking as 8.314 joules per Kelvin per mole. Simultaneously divide it with 1000, then only you'll get the answer in kilojoules per mole, right? If you are not dividing with 1000, the answer will be in joules per mole, right? Now people, the second one, 2.303 multiplied by 3. R value you'll be taking as 2 calories per Kelvin per mole. At the same time, I'll be dividing with 1000. Then only the answer will be in kilocalories per mole, right? Now, the calculation part is your job. Do it afterwards and kill the question. That's all. Perfect? Right, people? This is one question which I'm giving you as the homework, right? You can solve this question based on the same Arrhenius equation, or let me show you the solution as well. Well, this is the equation, my dear people. Log of K2 by K1 is equal to EA divided by 2.303 R, 1 by T1 minus 1 by T2, right? All the parameters are given to us. We are supposed to calculate the activation energy, put all the parameters in the equation, get the activation energy of the reaction, which you were supposed to calculate, right? Is every single thing clear? Is every single thing clear, my dear people? Are you guys ready for electrochemistry now? Are you guys ready for electrochemistry now? Let me know in the chats. Are you guys ready for the electrochemistry, people? Just give me a second. We shall be starting. Just give me a second, guys. Perfect then. So let's get going. Let's get started with the electrochemistry now. Let's solve the questions. Different types of questions which can be asked out of this particular chapter. It's a very simple chapter, right? Perfect. Let's see what all patterns, what all variety of question can be asked from this particular chapter. And I'm sure if you have watched the sessions of this electrochemistry in detail, I'm sure you can easily solve every question over here, right? So let's get going then. Let's get started with the first question, my dear people. The oxidizing power of the species. Oxidizing power. Well, let me tell you, a strong oxidizing agent has got the more oxidizing power. Strong oxidizing agent has got the more oxidizing power. An oxidizing agent is the one which oxidizes others but itself undergoes reduction, right? So that species which can undergo reduction easily, will be the better oxidizing agent, will have the more oxidizing power. Now the point is, which species can undergo reduction easily? Let me tell you, that species can undergo reduction easily, which will be having maximum standard reduction potential, right? Now compare all the standard reduction potential values. This 1.81, this is the standard reduction potential of CO tripositive. 1.61 standard reduction potential of C tripositive. Compare the values. I must say, this is the maximum value of standard reduction potential, that is for CO tripositive. If CO tripositive has got the maximum standard reduction potential, so it will undergo reduction easily, better oxidizing agent, more oxidizing power. Well, after this value, I'll be giving priority to this particular value, which is for Pb plus 4. So this is for Pb plus 4. After Pb plus 4, I'll be giving priority to this value, which is Ce plus 4. And after Ce plus 4, it's going to be Bi plus 3. This is the order of their oxidizing powers, my dear people, which you were supposed to calculate, right? So which option satisfies it? Check it out. It's option B, which is the correct answer of this particular question. Anisha is spamming the chat box with the wrong answer. Right? I love the confidence. Anyways, it's okay. Just try to learn out of mistakes. Going on to one more. The strongest oxidizing agent. Again, you need to check the SRP values, reduction potential values. Where do you see the reduction potential is maximum? In the third case, I must see the SRP value is maximum, that too for S2O dinegative. If the SRP value is maximum, it will be having maximum tendency to undergo reduction. The one which will be having the maximum tendency to undergo reduction will be the better oxidizing agent, will have the more oxidizing power, right? So the strongest oxidizing agent is S2O8 dinegative, my dear people, right? Perfecto. Calculate the EMF. Again, the cell is given to us. We need to calculate the EMF of this particular cell. Let's get to know how to calculate the EMF of the complete cell. It's a complete cell, my dear people. This is the salt bridge which we have used. On the left hand side of the salt bridge, there is anode, and at anode, you know, oxidation takes place, and oxidation means loss of electrons. So Sn is getting converted into Sn di positive. So the reaction at anode is something like this. Tin solid getting converted into tin di positive aqueous, and at the same time you'll be getting 2 electrons right here. This is the reaction taking place at anode. In the similar way, what is the reaction taking place at anode? At the cathode, my dear people. Pb di positive getting converted into Pb solid. So I must say this is the reaction. Pb di positive aqueous plus 2 electrons. It is getting converted into Pb solid, right? This is the reaction taking place at cathode. Since how do I get the net cell reaction? I just need to add the two reactions, but I'm not going to add the reactions unless electrons are balanced on both the sides, right? Since electrons are balanced, so I can add the two reactions. After adding the reactions, I'll be getting the net reaction as Sn solid plus Pb di positive aqueous. It gives Sn di positive aqueous. With this, you'll be writing Pb solid. So this is basically your net cell reaction which is taking place in the cell. Well, after getting the net cell reaction, I would want you guys to write the number of moles of electrons exchanged. So there are basically 2 moles of electrons which are exchanged in the net cell reaction. After that, I would want you to write the QC expression, which is nothing. I'll be starting with the products. It's going to be concentration of Sn plus 2 raised by its stoichiometric coefficient. This is in solid form, its hectomasses unity, divided by concentration of Pb di positive raised to the power its stoichiometric coefficient. Well, concentration of Sn di positive is given to me as 1 molar, divided by concentration of Pb di positive is given to me as 10 raised power minus 3. The value is going to be 10 raised power 3. So this is the value of QC, right? This is the value of QC, right? Yes? As simple as that. JSK, well, is that a compliment or you're telling me something different? I did not get it. Last name is saying, thank you so much, sir, JS Printer. That's great. Welcome, bro. Okay, so this is basically the value of QC, my dear people. After getting the value of QC, I would want you to calculate the E0 cell, which is basically equal to E0 of cathode minus E0 of anode. E0 of cathode minus E0 of anode, right? Well, my dear people, which one is cathode and which one is anode? Check it out. Check it out. This is basically your cathode and this is your anode. So I'll be writing the standard reduction potential of cathode. That means the standard reduction potential of lead, which is given to me as minus 0.13 minus standard reduction potential of anode. Standard reduction potential of anode is minus 0.14. The value comes out to be 0.01 volt, right? So this is basically your E0 cell. This is the E0 cell, right? Perfect. Well, my dear people, since you got the E0 cell, after getting the E0 cell value, I would want you guys to write the Arrhenius equation. So it's going to be E cell is equal to E0 cell minus 0.0591 divided by N, and it's going to be log of QC. Log of QC, right? That's what you do. Perfect. Well, E0 cell, you got to know already that 0.01 minus 0.0591 divided by N value is 2. Log of QC, QC is nothing, that's 10 raised power 3. Log of M raised power N is N log M. Take 3 in the front, it is 3 log 10. It is 3 log 10 is 1, right? Just solve this equation, get the answer in volts over here. That's going to be your E cell, which you were supposed to calculate as far as the question is concerned, right? Let me quickly know in the chats, people, if it is clear to everyone. Yes? Let me quickly know, my dear people, if it is clear to everyone. Yeah? Someone is saying, what is QC? QC is reaction quotient. The expression of reaction quotient is written in a similar way as you write the expression for equilibrium constant, right? It is just in the equilibrium constant, the concentrations and partial pressures of all the reactants and products are taken at equilibrium, whereas when you write the QC, the concentrations and partial pressures, they are taken at any stage apart from equilibrium, right? Perfect. Let's move on, my dear people, to one more question. calculate the oxidation potential of the half cell. This is the half cell which is given to us. We need to calculate its oxidation potential. Let's have a look how to solve this one. This iron is over here with 0 oxygen state. This iron is with +2 oxygen state. I need to calculate the oxidation potential of this half cell. So first of all, what I will do, I'll make sure the electrode, this half cell, behaves like the anode, and when it behaves like the anode, at anode oxidation takes place, your iron is getting converted into Fe di positive. So the reaction is supposed to be like this: Fe solid getting converted into Fe di positive aqueous, and with this you'll be writing 2 electrons. So you got to know 2 moles of electrons are exchanged in the reaction, right? Now just write the value of QC. It is equal to concentration of Fe di positive raised by its stoichiometric coefficient 1. This is solid, its active mass is unity, right? Now, my dear people, do we know the standard oxidation potential of the iron electrode? Do we know the standard oxidation potential or standard reduction? +2 to 0. +2 to 0. Decrease in the oxidation state means reduction. Means this is SRP. I do not need SRP. I need SOP. SOP, just reverse the sign. It is +0.44 volts. It is E0OX, right? Standard oxidation potential. Now, I'll be using the Arrhenius equation. I'll say oxidation potential of the electrode is equal to standard oxidation potential of the electrode, right, minus 0.0591 divided by N, and it's absolutely going to be log of QC over here, right? The equation is done and dusted. It's E0OX, which is 0.44 volts minus 0.0591 divided by N. N value over here is given to me as 2, and it's going to be log of QC. QC value we got to know somewhere. Concentration of Fe di positive, and Fe di positive concentration is 10 raised per -1, right? So this is log of m raised per n. Just take -1 in the front, log 10 becomes 1. So this is -1, minus becomes plus. Just solve this value, get the answer in volts. That is basically the oxidation potential of the half cell, which you are supposed to calculate. As simple as that, right? Perfect, guys? Perfecto. Moving on to one more. Another half cell is given to us. We are supposed to calculate its oxidation potential. Similar sort of question, similar sort of approach. This is not I'm going to do. This is something which you will be doing, and you will let me know its answer in the comment section of the video at the end, right? At the end of the session. Perfect. Right, people? Alright, let's try to solve one more question. What do you think about this one? What do you think about this one? The Gibbs free energy change in joules for the given reaction. Well, a reaction is given to us. We need to calculate the Gibbs free energy change. When the concentration is 1 molar, temperature is 298 Kelvin, right? So basically, you need to calculate the Gibbs free energy change at standard conditions. So delta G naught you need to calculate, which is going to be equal to minus NF E naught cell. Well, first of all, after looking at the reaction, I must say 2 moles of the electrons are exchanged in the net cell reaction, so N value is 2. After getting the N value, you should be getting E naught cell, which is basically equal to E naught of cathode minus E naught of anode. I'll be using the SRP of cathode, I'll be using the SRP of anode as well, right? Now check it out. Which one is cathode and which was anode? Copper undergoes oxidation, right? So this is going to be anode, and this tin is going to be your cathode. So standard reduction potential of tin of your cathode is minus 0.16. It is minus 0.16 minus standard reduction potential of anode. It's given to me as 0.34. The value comes out to be what? 0.44.5 volts, right? Minus times. So E naught cell you got. Since E naught cell also you got, so delta G naught you need to calculate, right? It's going to be minus N values 2. F value, you know, it's 96500 coulomb per mole, and E naught cell, you got to know it is minus 0.5 volts, right? So after putting all these values over here, you'll be getting the unit of this delta G naught in joules per mole. Perfect, right? Or let's keep it as in joules only, right? If you need to calculate in kilojoules, just divide with 1000, then only you'll be getting the answer in kilojoules as well. Perfect, the choice is all yours. Yeah? Simple, basic. Perfect. Moving on to one more question. Let's see what another question says. Calculate the reduction potential at the pH of 14 for the electrode Cu di positive, copper electrode at 25 degrees centigrade. KSP is given, E naught value is given. Let's try to solve it. Let's see how this sort of equation is to be solved. Let's see. See guys, we need to calculate the reduction potential of the electrode, right? We need to calculate the reduction potential of this particular electrode. So I'll make sure this copper electrode behaves like the cathode. Number one. When the copper electrode behaves like the cathode, so reduction is going to take place and the reaction is going to be Cu di positive aqueous plus 2 electrons gives Cu solid. This is your reaction, right? How many moles of electrons are exchanged? 2 moles of electrons are exchanged. So N value is 2 first of all. N value is 2. Now QC. How do I write the expression for QC? It's going to be 1, which is basically copper solid, its active mass is unity, divided by concentration of Cu di positive. Now the point is, I do not know the concentration of Cu di positive. So from where I'm going to get the concentration of Cu di positive? Well, for that purpose, pH of the solution is given to us as 14. Well, my dear people, pH of the solution is given to us as 14. If pH is given to me as 14, I must say H positive concentration is going to be 10 raised power minus 4 molar, right? Since the temperature is given us as 25 degrees centigrade, and you know, at 25 degrees centigrade, concentration of H positive multiplied by concentration of OH negative, it will be 10 raised power minus 14. So from here, you will be getting the concentration of OH negative, 10 raised power minus 14, divided by 10 raised power minus 14, the value comes out to be 1 molar. Now, what is the need of this OH negative concentration? I do not need the OH negative concentration. What do I need? I need the Cu di positive concentration, right? How do I get the Cu di positive? For that purpose, Ksp of CuOH whole twice is given. Well, CuOH whole twice, its Ksp is given. So first of all, how it's going to get dissociated? It's going to get dissociated in this way, Cu di positive aqueous plus 2 OH negative aqueous. If I write the expression for Ksp, it's going to be concentration of Cu di positive raised by stoichiometric coefficient, concentration of OH negative raised by stoichiometric coefficient, right? So Ksp value is given to me as per the question, that is 10 raised by minus 19. Concentration of Cu di positive I need to calculate. OH negative concentration is 1. So this is something which I'll be calling as the Cu di positive concentration. So it's going to be 1 divided by 10 raised by minus 19. The value comes out to be 10 raised by 19. This is the Qc value, right? Perfect. So Qc you calculated. Perfect. Well, after getting the Qc value, my dear people, I would want you guys to use the Arrhenius equation directly now, right? You can say reduction potential of the electrode is equal to standard reduction potential minus 0.0591 divided by N, and it's going to be log of Qc, right? Now all the parameters which you got, E naught already, that is the standard reduction potential of the copper electrode, which is 0.34. So this value is 0.34 minus 0.0591. N value you got as 2 log of Qc. Qc value is 10 raised per 19. 10 raised per 19 means 19 log 10. Log 10 is 1. So this term comes out to be 19, right? So multiply this term with 19 and solve the question. Get the answer in volts, right? That is going to be the reduction potential of the electrode which we were supposed to calculate, right? Perfect, guys. I'm sure every single thing is going to be clear till here. Yeah? Perfect. Find X. Have a look. What is X basically? X is the pH of the anodic container here, right? I'm sure there is one relation, my dear people. Orchid, I told you how to calculate the OH negative concentration, right? I've shown you. By using the ionic product of water, right? By using the concept of ionic product of water, that's all. Anyways, this is a simple question. You guys would have heard about the relation about the electrolytic concentration cell involving hydrogen electrodes. This is the electrolytic concentration cell involving the hydrogen electrodes. You need to calculate its EMF. 0.0591 multiplied by pH of anode minus pH of cathode, right? It's a simple, guys. Its answer will be 4. Have a look. E cell is equal to 0.0591 pH of anode minus pH of cathode. pH of anode is X, right? And pH of cathode is 0 because H positive concentration of cathode is 1 molar. So minus log of 1 is 0, right? So this term is 0, X value directly coming out to be 4. Yeah? Okay. How much current is required to produce H2 gas? So you need to produce H2 gas at the rate of 1 milliliter per second. So how much volume of H2 gas has to be released? Volume of H2 gas which must be released is 1 milliliter. And in how much time it has to be released? In 1 second, right? 1 ml of H2 gas has to be liberated in 1 second. So if I ask you at STP how many moles of H2 are supposed to get liberated? Volume divided by 22400. these many moles of H2 are supposed to get liberated in 1 second, right? If I ask you what is the n factor of H2, it is basically equal to number of moles of electrons exchanged, that's 2, divided by stoichiometric coefficient of H2 is 1. So 2 divided by 1 comes out to be 2. I'll be using a simple formula of the Faraday's first law. I'll say number of moles of H2 liberated should be equal to I multiplied by T. This is supposed to be the n factor of H2, and over here it should be 96500. Right? So how many moles of H2 are supposed to get liberated? It's 1 divided by 22400. Perfect. Is equal to 1 divided by n factor of H2 is 2. Wait, what did I do? 1 divided by 22400. I, current, I need to calculate. Time, 1 second. N factor of H2 is 2. Multiplied by 96500. When you solve this, as far as I remember, the value comes out to be 8.61 amperes. So this much current is used to liberate H2 gas at the rate of 1 ml per second, right? So my dear people, this was the last question of the night session. One question I'm going to give you as the homework. Please and please do give it a try and let me know its answer in the comment section of the video. This is the similar sort of question which you need to solve, and let me know its answer in the comment section. Okay? Well, tomorrow on the same channel, we'll be doing the formula revision, my dear people, right? Formula revision. All the formulas which are there in chemistry, I'll be giving it to you in one session, which will be just for 1 hour, right? Tomorrow at 9 p.m. sharp on this particular channel, we shall be doing the formula revision. Whatever, because majority of the questions from your physical chemistry will be directly formula based in your NEET examination, right? So that formula revision is going to be valid for both JEE as well as NEET 2022 students. So you guys can join in tomorrow. It's going to be fun, right? And all the formulas I'll be giving you in the handwritten form. Perfect. So with this, I'll be taking a leave here. I'll see you guys tomorrow at the same time. If you have not liked the video yet, please do like the video, share the video with all of your friends, and do subscribe to the channel, right? It was nice meeting you. See you tomorrow at the same time. Take care. God bless you all and love you all. Bye.